Hello, everyone. Welcome back to this week's algebraic graph theory seminar. This week, Sam Spiro, he's going to talk about new eigenvalue bound for the fractional chromatic number.
Okay. Yeah, thank you all for coming here. I just want to say everything that I'm going to talk about is based off some recent joint work with Krystal Guo. So as the title of my talk might suggest, we're going to be talking a lot about eigenvalues and chromatic numbers. So first of all, throughout the talk, I'm going to let lambda I denote the ith largest eigenvalue of the adjacency matrix of some graph. As I'm sure many of you know, these eigenvalues tell you a lot about the combinatorial information of your graph. One such result is due to Wilf, which shows that the chromatic number of a graph is at most 1 plus the size of the largest eigenvalue. And this is an improvement over the trivial combinatorial bound of 1 plus the maximum degree of the graph. There also exists a spectral lower bound for the chromatic number of a graph due to Hoffman, which is 1 plus the largest eigenvalue of the graph divided by the absolute value of the smallest eigenvalue of the graph, or equivalently the negative of it. So these are perhaps the two best well-known spectral bounds of the chromatic number. But there exist some others, and one I want to highlight involves two quantities called S plus and S minus. So S plus of some graph G will denote the sum of the squares of all the positive eigenvalues of your graph. And similarly, S minus of G will denote the sum of the squares of all the negative eigenvalues of your graph. And these concepts were introduced by Helfig and Witchen, and they conjectured that there exists a bound on the chromatic number that you can write in terms of these quantities. And this was proven a few years later by Ando and Lin, who showed that the chromatic number of a graph is always at least 1 plus the ratio of these S plus and S minus quantities. So this is all well and good, but why might we care about this? So first of all, this bound is best possible in a number of cases. So for bipartite graphs, it's well known that the spectrum of these graphs are symmetric, in that when you have lambda as an eigenvalue, you also have negative lambda. So this implies that for bipartite graphs, S plus is equal to S minus. So these ratios are all just 1. You get a lower bound, the chromatic number of 2 in this case, which is indeed true for bipartite graphs. Similarly for cliques, the spectrums for those are n minus 1 with multiplicity 1 and negative 1 with multiplicity n minus 1. So this S plus quantity will be n minus 1 squared, while S minus will be n minus 1. So the ratio here will be n minus 1, in total giving you a lower bound, the chromatic number of n, which is again type. And it turns out it's also type for some other things like the Paley graph on 9 vertices. But still, this may not be necessarily convincing that this is a useful bound, because, as I mentioned before, we have this other bound by Hoffman, which is also type for bipartite graphs and also type for cliques. So it could just be the case that these bounds here are just weaker versions of Hoffman's bound, which wouldn't be particularly interesting. But it turns out that these bounds are incomparable with each other. In particularly, if you look at all of the graphs between 5 and 8 vertices, which are connected and non-bipartite, then this Ando and Lin bound does better than Hoffman's bound for almost all of the cases. So about 11,000 out of the 11,800. So at least for small graphs, this bound does do better than the more standard bound of Hoffman. So this is indeed a new and useful. It's also useful if you care about these S plus and S minus quantities. So Helfig and Witchen conjectured that for connected n vertex graph, both these S plus and S minus quantities are always at least n minus 1. The rough motivation here is that if you have a tree, then S plus and S minus are both equal to n minus 1, because they're bipartite graphs, so it's equal to the number of edges. And so in the case for trees, this bound is tight. And similarly for cliques, the S minus quantity is exactly n minus 1, and S plus wins by a mile. So this conjecture is true for trees and for cliques. So it's somewhat intuitive that it should also hold for everything in between. But at the moment, this is still an open problem. But using this result with Ando and Lin, Helfig and Witchen observed that you can conclude that this result is true for regular graphs of G with degree at least 3. Let me walk through that. First of all, if you just have a clique, it's easy to prove directly at the result. So we can assume our graph is not a clique, and by our degree at least 3 condition, it's also not going to be a cycle. So by Brooks' theorem, the chromatic number of our graph is going to be at most the maximum degree of the graph, which in this case is T. And by Ando and Lin's result, this quantity is going to be at least 1 plus the ratio of S plus over S minus. We can just bring that into one common fraction. And now S minus plus S plus is just the sum of the squares of all of the eigenvalues of the graph, because S plus is just the squares of the positive eigenvalues, S minus is the squares of the negative ones. So because we have the sum of the squares of all the eigenvalues, well known, this is going to be twice the number of edges in our graph, which in this case, because we're a regular graph, is exactly D. And now if you maneuver things around, you get that S minus is at least, which is even better than we were trying to do. And the exact same argument also works for S plus. So this gives a very short proof of like a very large class of graphs for which this conjecture is true, and shows that if you want to try and disprove the conjecture, you somehow have to look at fairly unbalanced graphs. So again, this is Ando and Lin's result, which hopefully at this point I've convinced you is like of relevant interest. And the main results I have with Krystal is showing that this exact same lower bound holds not for the chromatic number, but for the fractional chromatic number, which I'll recall in a moment. But the important thing is that this quantity is always at most that of the chromatic number. So this is, and often, and in many cases, substantially smaller. So this is can be seen as a significant generalization of Ando and Lin. But let me just pause briefly here and just ask if there's any questions about any of the notation or anything else that's happened to this point. Okay, cool. So yeah, let me define what the fractional chromatic number is. And at least in my mind, there's two kind of natural-ish ways to approach this. One is in terms of the coloring procedure. So on the left here, I have a usual coloring of C5. And it's a proper coloring in that if I look at any edge, if I see any red at one endpoint, I don't see any red at the other endpoint. A fractional coloring is very similar, except instead of coloring each vertex a single color, I can color it, half red, a quarter blue, a quarter green. I can mix and match colors within a single vertex. And a fractional coloring will be proper if whenever I look at an edge, whenever I see some red on one end, I don't see any red on the other. So it's a somewhat natural generalization. And the weight of this fractional coloring, we observe that there's 1, 2, 3, 4, 5 distinct colors used, but each color is only used at half weight for any given vertex. So because of that, we'll consider each of these colors only a half color. So in total, the number of colors here is only going to be 5 halves, as opposed to what you get from this usual proper coloring, which has weight 3. So these by considering these half colorings and smaller things, you can get smaller chromatic, smaller color in some. So this is one way you can think about the fractional chromatic number. If you didn't understand what I said, that's fine. I'm going to completely ignore this, but just wanted to mention it for completeness. The perspective we're going to take for the rest of the talk is in terms of homomorphisms to Kneser graphs. So Kneser graphs, I'll denote by KVM, are graphs whose vertex set consists of all n element subsets of some ground set of size V, where two sets are going to be adjacent to each other if and only if they're disjoint. For example, here I have a picture of A5, 2. So each vertex is a 2-element subset of some 5-element ground set, and where we have 2 vertices adjacent to each other if and only if the corresponding sets are disjoint from each other. In particular, this Kneser graph is the Pearson graph, and many nice special graphs end up being special cases of Kneser graphs. So it's a very nice family. And the other concept we'll need is that of a homomorphism, which I'll recall is just the map from the vertex set of one graph to the vertex set of another graph, such that edges. I'm going to introduce some slightly non-standard notation and say that given some graph G, we'll let capital Phi be a set of graphs H, which G has a homomorphism. So with all this established, we can give an equivalent definition of the number. though it's certainly not obvious at first glance that they should be the same, which is that the fractional chromatic number is the minimum ratio V over N, where these Vn pairs range over all Kneser graphs, which your graph G has a homomorphism to. So that's a bit of a mouthful and a bit strange looking as well. Perhaps one way you can kind of think about this is going back to the usual chromatic numbers, where it's not too difficult to show that the chromatic number of graph is the smallest R such that your graph has a homomorphism to KR. And that's because a proper coloring of your graph G, a proper R coloring of your graph is the same as a homomorphism to KR. You just take the R colors, map each of them to a distinct vertex of KR, and the properness condition is equivalent to saying that edges map to edges of KR. So you can think of the chromatic number as the smallest clique, which you have a homomorphism to, and analogously, the fractional chromatic number can be thought of as the smallest Kneser graph, which you have a homomorphism to, in some sense. So yeah, this is a fractional chromatic number, and this is our result again. And the way we'll actually prove this is by proving a slightly stronger result, which says that whenever you have a graph G, which has a homomorphism to an edge-transitive graph H, and the ratio of the largest eigenvalue of H to the smallest eigenvalue of H is always at least these S plus S minus ratios. And the reason this implies our main theorem is because, again, the fractional chromatic number can be written as this ratio amongst all Kneser graphs we have a homomorphism to. It turns out that's not obvious at first glance, that these ratios V over N can be rewritten as 1 plus the size of your largest eigenvalue divided by the size of your smallest eigenvalue. And now, because Kneser graphs are edge transitive, we can lower bound this quantity by these S. So this theorem here is really what we're going to prove in order to get our ultimate result about the fractional chromatic number. Again, let me just pause briefly to see if there's any questions about the fractional chromatic number or this approach that we're considering. Okay, cool. So let me talk briefly about some additional applications you get from our improvement over Ando and Lin's results. So here I've stated the theorem, and here I've stated an equivalent version, which is again just follows from S plus plus S minus being twice the number of edges of your graph. So one thing that one can prove, which Krystal is currently working on with another group, is that for the N cycle, it satisfies this conjecture that S plus S minus is at least N minus 1. If you recall, Ando and Lin's result proved this for all regular graphs of degree at least 3, but the proof really broke down for cycles. So this, our result gives a quick proof of this case. So let's see it. First of all, if you have an even cycle, your bipartite graph S plus equals S minus, and everything is even. So for odd cycles, though, this lower bound of ours gives you exactly 2n over S plus S minus for the fractional chromatic number. And it's well known that the fractional chromatic number of an odd cycle is this quantity here. And if you just rearrange things, you get exactly that S plus S minus is at least N minus. And I'll note that you can prove this result directly for the cycle without needing to invoke our machinery, just by, we know what the eigenvalues are for an odd cycle, and you can just do some calculations, but the calculations are not trivial by any means. And this is definitely the fastest proof that I'm aware of that does this for a cycle. Similarly, we can get some mileage out of our stronger results about homomorphisms to edge-transitive graphs. Again, in this other group that's forthcoming, they proved that if you have a connected unicyclic graph with a cycle that's pretty large, then again, this S plus S minus conjecture holds. And the way they do this is a unicyclic graph has a natural homomorphism from itself to the cycle it contains, and cycles are edge transitive. So this result implies, and you get some bound on S plus S minus, which ends up being good enough when M is sufficiently large. And the nice thing with this result is, if you recall, for trees, both S plus and S minus equal N minus 1. So it seems somewhat plausible that if there's a counterexample to this general conjecture of connected graphs having both these quantities at least N minus 1, it might fail for unicyclic graphs because you just add one edge to the tree and maybe you just tilt one of the eigenvalues down slightly and you end up failing. So this result shows at least that this isn't the case if your unicyclic graph has a large signal. And lastly, I'll talk about just philosophically what's going on kind of with this term here. The point is that you can extend this theorem slightly. For example, it holds trivially if you allow H to not just to be bipartite, even if it's not edge-transitive. And there's also a couple of other kind of trivial graphs that for which this holds once you know it holds for edge-transitive. But this result doesn't hold for arbitrary H. And in fact, it doesn't even hold if you replace edge transitivity by vertex transitivity. In particular, if you take G to be a triangle and H to be the complement of C6, this is a vertex transitive graph, but not edge transitive, and the inequality here does not hold. So the point is that this theorem is sharp in the sense that you can't push it to the next level of symmetry. You can't say that this holds for vertex transitive graphs. It's important that we're doing edge transitive. Okay, I think that's all I want to say before starting the proof. But again, let me just pause briefly to see if there's any questions. Okay, cool. So let me talk briefly about the proof, or maybe not briefly, fairly long about the proof. So throughout, I'm going to be talking about the Frobenius norm whenever I write the norm symbol. So for any matrix X, this is just the sum of all of its entries squared. And if we further have X a real symmetric matrix, this will be the trace of X squared, or equivalently the sum of all its eigenvalues. And now the first thing to think about when trying to prove this result is that these S plus S minus things are kind of strange. It's not immediately obvious how they would even show up in a proof. But one idea you can do for this, which I believe originates with Ando and Lin, is you can take the spectral decomposition for A, and then write A as the difference of two matrices, X and Y, where X is the part of the spectral decomposition of the positive eigenvalues, and Y is the negative of the part with the negative eigenvalues. And the advantage in doing this is, first of all, X and Y are PSD matrices, which is always nice. And perhaps most importantly, the norm of X squared, which is in this case just the sum of all eigenvalues squared, is exactly the sum of all the positive eigenvalues of A squared, or the sum of the squares of all positive. And similarly for Y squared, its norm is S minus. So the point now is that if we want to prove some upper bound on the ratio of S plus S minus, which is ultimately what we want to do, it's in fact equivalent to prove an upper bound for the norm squared of X in terms of the norm squared of Y. And this formulation is perhaps more amenable to standard analytic and linear algebraic manipulation. So this is ultimately what we're going to try to prove. So towards this end, we recall that we're going to try and prove our second theorem, which is if you have a homomorphism G to an edge-transitive graph, then you have some inequality. So let's fix what this homomorphism is. And given this, whenever I have a matrix X indexed by my big graph G, I'm going to define a block partition as follows. So if we have two vertices U, V, and H, we'll let the U, V block of X be the submatrix whose rows are indexed by the preimage of U and columns are indexed by the preimage of V. Again, one way to think about this is if we're trying to do Ando and Lin's proof for the chromatic number, we're going to consider homomorphisms to cliques, in which case these preimages are exactly the color classes of our proper color. So this is in some sense just a generalization of that idea, but in this more general setting of homomorphism. And now with this in mind, kind of the main technical result that Ando and Lin proved, which we'll go through slowly, is the following. So say we have some homomorphism from G to H, and let's say we have two matrices X and Y, which satisfy the two key properties. The first is that their product is 0, and the second is that their UV blocks are equal to each other whenever UV is not an edge. If we have this, and if we happen to have some strange-looking bound on the norm squared of X, then we end up getting some appropriate bound on the norm squared of Y. So again, this is a lot, but let's first perhaps just digest these to hypotheses here. The observation is that if we have a non-edge of H, then the UV block of the adjacency matrix is going to be 0. The point is that if there was some edge in this UV block, then you would have to map to an edge of H because you were considering homomorphism. This is just the homomorphism property, basically rewritten. So now, whenever we have two matrices X and Y with A equal to X minus Y, we're going to get for free that their UV blocks have to be equal to each other in order for this to happen. And moreover, if we choose X and Y to be exactly those two matrices I suggested on the previous slide, we also get that their product is 0 because their eigenspace decomposition has orthogonal eigenvalues. So the point with this lemma is that if we choose X and Y to be these two things here, then these two main hypotheses will automatically be set. So really, it remains to say that, okay, in this setup, to prove some weird bound on the norm squared of X, and then we'll for free get exactly the kind of bound we're looking for. So I'm not going to go through the proof here. I will say it's fairly elementary. It requires two uses of Cauchy-Schwarz inequality and some careful arithmetic manipulations for about a page length. So the real ingenuity is coming up with that you want to prove something like this. But once you know you want to prove something like this, the proof is not terrible. Okay. So again, we've reduced our problem to bounding the norm squared of these X matrices that arise from the spectral decomposition. And really the only key information we know about X is that it's going to be PSD. So this is, we want to prove something like this. In particular, Ando and Lin did this when this H graph is a clique on R+1 vertices. So unwinding what this inequality says in this case, we want to prove that if you have a PSD matrix with blocks indexed from integers 1 to R+1, then the norm squared of X is at most R+1 times the norm squared of all of the diagonal blocks of this matrix. So the point is, if we go back here, here the sum is over all non-edges of the graph H that we have a homomorphism to. And if our graph H is the clique, the only non-edges are kind of the diagonal places where the U equals V. So this is now a purely linear algebraic thing. It doesn't have any graphs, at least up front. And the proof isn't too bad. So let me walk through that. So first of all, X being a positive semi-definite matrix means every principal submatrix is. In particular, if we take our favorite U and V, this block matrix has to be PSD. And now I claim that this inequality holds with respect to the norms. The point is that if these were 1-by-1 blocks, then for this to be PSD, our determinant has to be non-negative. And this statement here, in the case of 1-by-1 blocks, is exactly saying that the determinant is non-negative. And this also holds for larger blocks, which you can use a sort of reduction argument to get here. But for the moment, let me just push that under the rug. From here, we can use the AM-GM inequality to say that this is the average of the squares of the diagonal blocks. So now what we can do is we can upper bound the norm squared of the off-diagonal blocks, because for each of these off-diagonal blocks, we can use this to replace them with their corresponding diagonal blocks. And if you just count how many times each of these diagonal blocks show up, you get exactly this quantity. And once we have this, we can, we're basically done. So the norm squared of X is equal to the sum of the norm squares over the diagonal blocks plus the norm squares over the off blocks. And now we've just upper bounded this the off diagonals in terms of the diagonals, and replacing that gives you exactly what we want to prove. So if you didn't follow any of that, that was fine. I just really wanted to express that proving this is not too difficult. It's all I've up to this, except for this little thing here, which is not too hard to prove. I have not really hidden anything. This is all that you need to prove the lemma. It all fits neatly onto a single slide. And for our result, we need to prove an analog of this, but not just for the clique, but for arbitrary edge-transitive graphs. And in particular, we're going to prove this result here. So let me say two comments about this. First is that I've secretly snuck in the word vertex transitive into the hypothesis of this lemma. And it might seem kind of strange since I made a whole big deal about how a result doesn't hold for just vertex transitive graph. But the point here is that there are two kinds of edge transitive graphs: those that are vertex transitive and those that are bipartite. Those are the only two cases. And if we have an edge transitive graph which is bipartite, then the result is trivial, because for bipartite graphs, s plus equals s minus, and you can just solve the problem directly. So there's no harm in us really just looking at edge transitive graphs, which are also vertex transitive. The second thing I want to note is that although this part of the proof for Ando and Lin was like relatively easy, this part will not be so easy for us in the generality of edge transitive graphs. And this is perhaps suggested by the fact that, again, this statement does not hold if you delete the word edge transitive. You somehow have to crucially use that in your proof. Otherwise, you will not. This result can't possibly be. Okay, and the way we'll prove this is through about 3 reductionary steps to somewhat simpler problems. So the first reduction step is to consider kind of a smaller matrix to work with. So we're going to let Z be the matrix whose UV entry is just the norm squared of the UV block of X. This will kind of clean up all this like norm notation. And in particular, I claim that to prove this lemma here, it suffices to prove this inequality here just in terms of the entries of the UV, where Z is a non-negative PSD. The point is, if we know this is true and we're given some X of this form, then we can define Z exactly like this. Z will fairly obviously be non-negative because it's going to be squares. All its entries are squares. It's also not too difficult to show that if X is PSD, Z is also PSD. So in some sense, this is a simplification of the problem. And from here, we're going to really use that we have an edge-transitive graph. And to do this, we're going to need the following technical result, which is that if you have an edge-transitive graph H, then there exists a nice family of graphs with the following 4 crucial points. The first is that our graph is in this family. Let's just say it's the last one in the family. The second is that for any pair of distinct vertices on V of H, then there's a unique I such that UV is an edge of the graph H. So what this is just saying is that these HI graphs form a partition for the peak on V of H. The third thing is that every automorphism of H is going to be an automorphism for each of the HI graphs. This is saying that each of the HI graphs are at least as symmetric as our original graph. And lastly, for every pair of edges in one of the HI graphs, there exists some automorphism of H, which maps UV to X. So this says that all of the graphs in this family are edge transitive, and moreover, their edge transitivity can be exhibited by only using automorphisms of H, which again are automorphisms of each HI by this condition. So this perhaps seems a little strange here. So maybe we'll consider a concrete example. If H is the Kneser graph, then this statement holds if we let HI be the graph whose, again, same ground set of n element subsets of V, where we make 2 graphs, 2 sets adjacent to each other if their intersection has size n minus I. So for the experts in the room, you may recognize that this is exactly the Johnson scheme, which is a special case of what's known as an association. So association schemes are very powerful objects in the study of spectral graph theory, and they don't always. There's not always the case that every graph lies in an association scheme, but when it does, you gain a lot of power. And what this result says is that every edge-transitive graph, in some sense, belongs to a weak association. It doesn't have all the properties that you would like to have in an association scheme, but it does have some of these properties here, which in particular hold for the Johnson scheme. And in fact, the way we kind of stumbled across our main theorem is we were trying to prove our result just for the fractional chromatic number, and we were using some arguments based off of the Johnson scheme, and then realized in retrospect we didn't actually need that much from the Johnson scheme. We really only need these properties here, which turn out to be equivalent to your graph being edge transitive. So if you don't know what association schemes are, you could just blot that all out. If you do know what association schemes are, you may find some of the arguments we're going to use to be motivated in this spirit. But anyway, this is the technical lemma, which says edge-transitive graphs belong to this nice family of edge-transitive. So with this in mind, we're going to let AI denote the adjacency matrix of the graph in this family, and we'll let A naught be the identity. So now we're going to do one more reduction, which says that to prove this result here for non-negative PSD matrices Z, it suffices to show this for non-negative PSD matrices, which are in the span of these AI matrices. Or again, if you're familiar with the association scheme language, it's saying that Z is in the scheme of these H's. All right, and the way we do this is we consider a sort of average version of any Z that we're given. So in particular, we're going to define Z bar by taking each automorphism of H and then conjugating Z by the associated permutation matrices, and then summing up over all of these permutation matrices and then dividing out by the number of terms in this sum. And one can check that this Z bar matrix has basically all the properties we want. It's PSD because the positive sum of PSD matrices. It's also similarly non-negative. The sum of all its entries is the sum of all the entries of the original matrix. Similarly, the sum of all the entries over the non-edges of H is the same as the sum of all the entries over the non-edges of H in the original thing. And crucially, this new average matrix is in this. So accepting these claims, once we know that this bound holds for Z bar, it also automatically holds for Z. And I won't go through the details on how you verify all this, but I assure you it's not terribly difficult. And I forgot to just briefly mention that also proving this lemma here is not too hard. So the way you prove this is you consider the set of all pairs of distinct vertices of H, and then you take the action of the set by the automorphisms of H, and then you just take the orbits of this action. And these orbits, you very quickly can verify satisfy all of these conditions. So this is very easy to prove again once you know this is what you're looking for. Then I just want to put that out. Yeah. Here's the next reduction we did. And now we finally reduced the problem to something you can actually solve by hand. Which again, reminder is showing that if you have a PSD non-negative matrix in this nice pseudo adjacencies, pseudo association scheme, then you have this weird inequality. So to do this, we're going to fix an eigenvector of our original graph H, which we're calling, we're denoting by AN. And this eigenvector is going to be associated to the smallest eigenvalue of AN. Then because Z is a PSD matrix, this quantity here is going to be non-negative. And because Z is in our scheme, we can rewrite Z as this linear combination of these AI and apply the X's individually to each of them. Now, for any given AI, this quantity here is going to be at most the size of, I should say this is a unit eigenvector, but whatever. So each of these quantities here is going to be at most the largest eigenvalue of AI, if we're unlucky. With the exception of the case I equals n, where we know by construction of X being an eigenvector, it's going to be exactly lambda min of AN. Rearranging things, we get that the sum over this vi lambda max quantity over all I non-delta n is at least Zn times the absolute value of this lambda min condition. And now I claim that I can rewrite this sum here, or no, I don't claim that. I claim this thing, which is that each of the AI matrices, which are just 0, 1 matrices, has exactly this many 1 entries. So the point is that if you carefully look at so if you recall actually that H we're assuming is vertex transitive. And basically by the conditions I put on these HI graphs, they're also all going to be vertex transitive. In particular, they're all going to be regular graphs. And they're going to be regular of this degree, lambda max of AI. So if you look at every row of each of these matrices, you're going to see exactly this many ones. So in total, the number of ones is exactly this quantity here. All right. So now I claim I can rewrite this inequality above in this form here. So first of all, the sum of all the entries, I can just take the sum of all the entries of each of the AIs times ZI, because we're in the scheme. And the number of the summing over all the entries of AI is just exactly this thing here, the number of 1, which we then scale by the coefficient. So this is just the sum over all of the entries of Z. Similarly, if we look at the sum over all the entries that are not edges, we just get the exact same sum here, but we don't look at I equals n. The I equals n case is again corresponding to the adjacency matrix of our original graph. So if we want to look at all the non-edges, it's exactly just summing over all the terms where this an is not. So this is just exactly a reformulation of this once you realize all of our graphs are regular. And now I claim that just some simple algebraic manipulations gives you the result. In particular, we see that this sum on the left here is almost the same as this 1 times this sum here. They're only missing the last term. So you can subtract this on both sides and just get Zn times lambda max CH. Then you can upper bound this times this thing here by using that this sum is at least this here. So you can replace this sum by this quantity here. The lambda mins cancel, and you get exactly the same thing on both sides. So again, I don't expect anyone to necessarily follow all those steps. The point is that essentially all of the details of proving this lemma are like truly here, and it's like now not that difficult to prove once you know this is the right statement to prove. So let me just briefly summarize what we've done now. So first we had this idea based off of Ando and Lin of rewriting A as x minus y for these positive and negative parts of the spectral decomposition, which reduces the problem of upper bounding s plus in terms of s minus, in terms of upper bounding the norm squared of x, in terms of the norm squared. We then use this result of Ando and Lin, whose proof I admitted, which said that proving something like this, it suffices to prove some norm inequality for PSG matrices X in terms of our graph H that we have homomorphism to. We then did a series of reductionary steps for this problem. We replaced X by the matrix where it can code this norm squared. And then we did an averaging argument based off of this pseudo association scheme to reduce the problem to proving an inequality for PSD matrices, which are the span of these AI matrices. And finally, we just proved this directly using Rayleigh quotient. This proves the main theorem that we wanted, which implies the fractional result. So let me just pause briefly and see if there's any questions about any step of this proof, or again, the notation, or again, anything else. Okay, so let me talk a bit about some future things one might be able to do here. So again, this is just a restatement of our main result, the lower bound of the fractional chromatic number, which is always at least as good as the chromatic number. So there's a couple different ways you could try and take this further. So one you could ask is, okay, we improved this chromatic number bound to fractional chromatic number. Can you prove this even further? So one particular thing you could try and do, as was asked by Nexton, Elf, and Witchen, is whether or not this same lower bound holds for the vector chromatic number. And if you don't know what a vector chromatic number graph is, it's fine. The important thing is that it's a lower bound for the fractional chromatic number. So if true, this would be an further improvement of our result, and computational evidence suggests that this could be true. And you could try, instead of proving this immediately, you can maybe try and prove some related, weaker results, namely that the same bound holds for orthogonal rank or projective. And again, what these words mean, that's fine. This is one thing you could do, is trying to replace chi of f with something smaller. Another thing you could try and do is replace this s plus s minus thing with a different but related bound. In particular, it was conjectured by Elf and Witchen. You can lower bound the fractional chromatic number by 1 plus the ratio of the number of positive eigenvalues of G to your number of negative eigenvalues. So this looks very similar to our result. And in fact, you could consider a possibly even broader conjecture where these s pluses are the sums of the squares of the positive eigenvalues, while n plus is the sums of the positive eigenvalues raised to the 0th power. So you could maybe ask the same question where does this hold for any reasonable choice of sum all the eigenvalues raised to some rth power? Does this ratio hold? So this seems like a reasonable question to ask. But for both of these conjectures or problems, our methods fall somewhat short. So in particular for this question, as far as I know, there's no homomorphism interpretation for the vector chromatic number. So one has to go somewhat further than our homomorphism-based approach for this. And for this, there's kind of a roadblock, which is, if you recall, the way we proved our fractional chromatic number lower bound was we actually proved a bound in terms of whenever you have a homomorphism to some edge-transitive graph. And there's sort of a natural analog of this conjecture that you can make in that same sort of setting, where if you have a mapping to an edge-transitive graph, then you have some lower bound of something. However, that natural extension does not hold when you replace these s plus s minuses by n plus n minus. So in particular, our approach can't possibly work, or at least in the level of generality of edge-transitive graph. So this possibly suggests that instead of using these like weak association schemes, you would have, if you could prove this using our approach, you'd have to use like genuinely the full power of the Johnson scheme for this to go through. And it's plausible that something like that could work out. Another thing I'll mention is this, again, this conjecture of Alpha and Witchen about s plus and s minus both being at least n minus 1. As I mentioned, our results give some further progress towards this conjecture, but still it's, as far as I can tell, very far from being so. It'd be great if some more significant progress could be made. And the last kind of possible approach I'll mention is a bit more pie in the sky. So given a family of graphs H, I'll define this H chromatic number of a graph be 1 plus the infimum of the ratio of this maximum minimum eigenvalue for all, as the infimum ranges over all H, which are in this family of graphs and which G has a homomorphism. So the rough thought here is that if H is the family of pleats, this exactly defines the chromatic number. If H is the family of Kneser graphs, this exactly defines the fractional chromatic number. So it might be interesting to study other families of graph H and seeing like what can be said about this kind of spectral analog of the chromatic number. In particular, our main result can be rephrased as saying that when H is the set of all edge-transitive graphs, this H chromatic number is at least this quantity here. And you could, again, once you have this formulation, you can ask to what extent is this general? What's the largest set of graphs such that this spectral bound, which holds for this family, also holds for the other family? And more generally, if I give you some bound which holds for the chromatic number, the fractional chromatic number, you could ask what's the largest family of graphs H such that this bound continues. In particular, you could ask, what's the largest set of graphs H such that this Hoffman bound holds? Again, it holds for the set of Kneser graphs, and it's not immediately clear what else could be. I think that's all I wanted to say, so I'll end the talk.